All right. Hopefully I can do chapter 6 and get it recorded this time. And that's going to be due Sunday, assuming I got my dates right again. I'll have to check those. So we talked about gases. Now we're going to talk about solutions. What's a property of a solution? It's a homogeneous mixture of two or more substances. The solute is the component of a solution that's present in lesser quantity. The solvent is the component that's present in a larger quantity. And if the solvent is water, it's an aqueous solution. So if I put a teaspoon of salt in water, the salt is the solute, the water is the solvent, and since it's water, it's an aqueous solution. Solutions can be liquids as well as solids and gases. We normally think of them as liquids. So air, oxygen, and several trace gases are dissolved in nitrogen. So nitrogen's the solvent. That's the major component of air. Alloys, mixtures of metals dissolved in each other. So brass, bronze, pewter. We can also have liquids dissolved in solids. We can dissolve liquid mercury in solid silver. It's quite common. Anybody know where we find that? If I said the word amalgam, would you know what I was talking about? Yeah, dental fillings. The silver dental fillings have mercury in them. There was a push a couple years ago for people to go have them all, because it's got mercury, obviously mercury's toxic, have all their fillings removed and replaced with ceramic. But I mean, people have had mercury, silver and mercury fillings for generations. And there's no proof that it causes any toxicity. So we're going to actually focus on liquid solutions because most important chemical reactions take place in liquid solutions. What is a property of a solution? Clear, transparent, no visible particles. Sometimes you think you have a solution and you don't. We'll talk about that later. It may be colored or colorless. So when we say clear, it doesn't necessarily mean clear like in glass. It could be tinted like in glass. If you have ionic compounds, they dissociate in water to give you electrolytes, and we talked about electrolytes before. Usually molecules don't dissociate, so they form non-electrolytes. Volumes of solute and solvent are not additive necessarily. So 1 liter of ethanol plus 1 liter of water does not give you 2 liters of solution. So if I took 50 mils of ethanol and 50 mils of water, mixed it, poured it in a graduated cylinder, it'd actually be about 98 mils. That's because the hydrogen bonding forces between the two are so strong, it just kind of shrinks the space between them. So it's not always additive. Colloidal suspensions, come back up here, contain solute particles which are not uniformly distributed. Due to larger size of particles, they're about 1 nanometer to 200 nanometers. They appear identical to solution for the naked eye that you would look at it. Larger than 1 nanometer have a precipitate, and you can't always tell. So if you're working in the pharmaceutical industry, like a lot of your biotech industries, you may have a formulation that supposedly is a solution. But if you look at it closely, it's not a solution. Well, how can you look at it closely? I mean, your naked eye. So they use something called a Tyndall beam. It's a Tyndall effect. And here you have glasses of, or containers of liquid. We shine the light through it. Here you don't see the beam. Here you see the beam, right here. This is a solution. This is not. It's a colloidal suspension. So that beam shows you the difference. And that can be problematic because if you're marketing something as a solution and you have a colloidal suspension like that and it sits in somebody's shelf and they're supposed to take a teaspoon, most of the drug may be at the bottom of the bottle. So you're not getting what they're supposed to.
It's automatically not a solution because it's not homogeneous,
Right.
right? Because if you got colloids, it's automatic.
It's not a solution. It's not homogeneous. Yes, and it will settle over a period of time.
If they shake it out.
Well, yeah, that's why sometimes we'd have to put direction shake before using. Milk of magnesia, obviously, of course, it's not a solution. You can't see through it. It's opaque. But if you let it sit, or Pepto-Bismol, it'll settle after a while. You see this all the time. Okay, I would say spring break, but we didn't have a lot of sun during spring break. But if you're sitting home on a nice sunny day, laying on your couch watching TV, oh yeah, you got a nice, like you're looking now, nice clear air. Beam of sunlight comes through the room. All of a sudden, what do you see? Dust particles all over the place, right? Pollen particles, dust mites, old skin, which is mostly what it is. Okay, so that is a colloidal suspension. You see that a lot in evidence in the spring and the fall. You get up to come to class, you know, and the ground is warm and the air is cold. We end up with fog. That's a colloidal suspension. And you can see the Tyndall beam effect if you put your headlights on it, which is why you don't want to use your bright lights because it just bounces back more into your eyes. Or if you watch action movies on TV and the hero or villain's trying to break into the safe, it's just protected by a bunch of laser beam alarms or infrared alarms. They'd usually take a aerosol can and they spray it, and then all of a sudden you see the lights. That's how you can see, because normally you wouldn't see it. So if you're doing a laser show and there's actually no particles in the air, you would never see the light. So solutions, we talk about solubility. How much of a particular solute can dissolve in a certain solvent at a specified temperature? Okay, because it has to be at a certain temperature, because the solubility changes with temperature. What affects the solubility? The polarity of the solute and the solvent. The more different they are, the lower the solubility. So the rule of thumb is like dissolves like. Polar compounds dissolve polar substances. Water is polar, so it dissolves polar substances like salts, usually. Nonpolar solvents dissolve nonpolar compounds. So oil doesn't dissolve in water, but will dissolve in gasoline or paint thinner. So, you know, if you're painting and you're painting with oil-based paint, you can't clean your brushes in soap and water. You have to use paint thinner, gasoline, something like that. Latex, which is a water-based paint, you can use soap and water. So if you go to remodel your house, you said, I'm going to paint my kitchen cabinets, and they're old. A lot of times, in the old days, they use oil-based paint because it gives you a nice finish. If you go over with latex paint, it'll look good until you hit it, and it'll just peel right off because it doesn't mix. You have to do a certain treatment to it to get it to stick. You got to kind of sand it and treat it with something called TSP. Okay, temperature usually increases the solubility. So Easter's coming. If you want something to do with kids, make them rock candy. 3 cups of sugar and 1 cup of water. You got to take that 1 cup of water, start heating it on the stove, and add the sugar gradually, and eventually it'll go in. Take it till it boils. Be very careful because now you got a real thick syrup type mess. And after it gets to boiling, pour it into a glass carefully because it's very hot. Hang a string in there and let it cool slowly. As it cools, the solubility of the sugar decreases. It starts coming out of solution. It usually starts crystallizing on the string, and you get big crystals. That's rock candy. That's all it is. And give it to your kids, let them eat it, and run around like crazy for 20, 30 minutes until they drop over. Okay. Pressure usually has no effect on solubility unless you have a gas. The solubility of a gas in a liquid is directly proportional to applied pressure. Saturation. A saturated solution contains all the solute that can be dissolved at a particular temperature. So if you have a glass of sugar and a glass of water, and you add a teaspoon of sugar and you stir it, it dissolves. You add another teaspoon, it dissolves. There'll come a time when you add a teaspoon and it won't dissolve, no matter how much it just sits on the bottom. That solution is saturated. A supersaturated solution contains more solute that can be dissolved at the current temperature. Again, how do you do this? And I wish I had one here. This one, I'll show you an example. Let me pause this. So if excess solute is added to a solvent, some dissolves. At first, the rate of dissolution is large. So if you have a glass of water, the first time you add a teaspoon of sugar, it dissolves really quickly. Later, the reverse reaction, precipitation, occurs more quickly. So when you dissolve stuff and you get to a saturated point, so you have some sitting on the bottom, it's not done. What happens is some goes into solution and some comes out of solution. So at equilibrium, the rates of dissolution and precipitation are equal. There's some dissolved and some undissolved. So a saturated solution is an example of a dynamic equilibrium. So let me do this. 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 Okay. So you used to be able to buy, when I was a kid, these magic crystal gardens. And you'd get a little plastic tank and it would come with a little pouch of sodium silicate. And you'd pour that into water and you'd put that in the tank. Then there'd be a bunch of different colored rocks. And you'd stick those on the bottom. I'm not going to do all the colors, but say you had red, blue, yellow, and they're different minerals, different solubilities. And you'd walk away. What happens is some of it goes into solution. When it reaches its maximum, some of them starts precipitating out. And it tends to precipitate out back on the rock where it came from. So you come back after a couple hours and you have one that's this tall and one that's this tall and one that's this tall, like a little garden, rock garden. And it all has to do with that dynamic equilibrium of solubilities. And the sodium silicate makes it, the water, kind of thicker. So you can still find them if you look online. Yeah, magic crystal gardens or whatever they call it. Who knows what they call it now? But that's the principle behind that. What about gases? Henry's law. The number of moles of a gas dissolved in a liquid at a given temperature is proportional to the partial pressure of the gas above the liquid. What does that mean? That means the more you push on the gas, the more you can force it into the solution. So what happens, the gas solubility in the liquid is directly proportional to the pressure of the gas in the atmosphere in contact with the liquid. So if you go to your local bottling plant where they're bottling Coke and Pepsi or whatever, they want to get the carbon dioxide in there, they pump it in under pressure. So they get more carbon dioxide into the solution. So they push it in there, and they screw the cap on. Then they take it to your store, and if you have the 2-liter Pepsi bottle, you know, it's filled, there's a little space above. That's called the head space. So what's the bottle feel like in the store? It's rigid, right? It's real tight. So you take the cap off. Now all of a sudden your headspace becomes everything above it. So the pressure goes down. So the solubility of the gas goes down. So when you take the top off of a Pepsi or Coke bottle, excuse me, I don't know who you are. I thought it was my wife calling. But anyways, as you take the cap off the bottle, even if it was, shut her off anyways. Okay. It's my excuse. I didn't know who it was. What happens? Take the cap off a pop bottle. Do what? It fizzes and bubbles. Yeah, because you release the head pressure, so now the CO2 comes out, and there's where the bubbles come from. So, you know, if you go into like a fast food restaurant and you're getting Coke or Pepsi out of those machines and it's flat, you tell the guy he comes out with a big CO2 cylinder and sticks it in there. Because you have to put it in under pressure. You can't do it at atmospheric pressure. You can say to myself, well, I want to make soda. Okay, take water, put in some sugar, put in some flavoring. You can buy cola flavoring in the store. CO2, what's the source of CO2? Dry ice, right? Dry ice is solid CO2. You take a couple of dry ice, put it in there, you know, bubbles, and but you don't get enough in there to make it taste right. If you taste it, it tastes like garbage. Like when soda goes flat. Gases are more soluble at low temperatures. So now when they bottle it, they put it under high pressure, they do it cold. So they can get more in there. So usually late July or August, somewhere you'll read, somewhere usually North Carolina or somewhere, at some creek or little pond or lake, all of a sudden they'll find dozens, if not hundreds, of fish dead, just floating there. Why? What do fish need to live? Air. Well, they need water, but they had water because they're floating in the water. So what happens to the water in late July and August? It gets warmer. As it gets warmer, what happens to the oxygen dissolved in the water? It comes out. It gets less. So sometimes these fish find their ways in shallow water, and all of a sudden it gets real hot. The oxygen goes away. They die, and they just surface, float on their backs. Okay. So a lot of times if you're fishing, you know, especially in the dead of summer, they're in the deep water because that's where the oxygen is. How do we measure concentration? It's the amount of solute dissolved in a given amount of solution. And we see that in stores all the time. You buy a cleaner, it's 5% ammonia. You buy a cleaner, it's 10% ammonia. So you know which one has more ammonia in it, right? 10%, right? So the concentration of a solution has effect on its physical properties, melting and boiling points, and its chemical properties, solution reactivity. You can kind of predict which is going to react faster, concentrated or dilute. The what? Concentrated, yeah. Why? Okay, that's a lawyer answer. Okay. No, it's more. Okay. What do you need to have a chemical reaction between two molecules? They have to what? I'm over here and I'm over here. What do they got to do to react? They got to, right? They got to hit. So if I only had 5 people in this room and I blindfolded them and sent them around, if I had 100 people in this room and blindfolded and sent them around, which one would have more collisions? 100 people. So the faster the reaction, because you have more particles that can react. Okay? It's more concentrated, that's what you said, yeah. So we can calculate what's called mass volume percent. So it's a percentage problem. Part over the whole times 100, like any percentage problem you want to know. You want to know your APY, yeah, for your savings account. You know, you want to know how much is off on the purse you're going to buy a Coach or whatever. It's a percentage problem. Concentration is the amount of solute divided by the amount of solution times 100. So percent mass volume, this is used when you're dissolving a solid in a liquid, is grams of solute divided by milliliters of solution times 100. So if I take 5 grams of sugar, dissolve it in 100 milliliters of water, what's the percentage? 5 grams of sugar dissolved in 100 milliliters, give me 100 mils of solution. What's the percentage? Sugar. 5. It's 5 divided by 100 times 100. So that's all that says. So you can calculate pretty much everything. So calculate the percent composition, percent mass volume, of 200 mils containing 20 grams of sodium chloride. So it's 20 divided by 200 times 100. 10%. So you may see this a lot on, let's say, cough syrups. My little thing is trying to turn over here. Okay, so that's percent mass volume. Calculate the number of grams of glucose in 750 milliliters of a 15% solution. So we have 15%. We don't know how many grams of glucose, so that's the x, divided by 750 milliliters times 100. The glucose times 100 is equal to 15 times 750. X glucose is 113 grams. So given 2 out of the 3, you should be able to calculate the third. Okay, a lot of times you biotech people, you're going to need to calculate how much you need to add to make a certain percentage solution. So you'd use this calculation. Nursing people, you may need to know how to make a certain percentage solution. Yes?
But this doesn't apply when the solvent and solute are not additive? Like example you gave when you said it would be 98.
Oh, when the 2 aren't additive, like that 2 liquids. Well, first of all, that'd be volume. But what you would do there is you would add, let's say you're going to do 10% ethanol in water. You're going to make 100 mils. So you know the solution has to be 100 mils. 10 mils of that have to be ethanol. So you'd add the 10 mils of ethanol, then you dilute it to 100 mils with water. So technically, you'd be adding a little bit more than 90 of water. We have mass percent. That's where you're adding a solid to maybe another solid. So again, it's grams of solute over grams of solution times 100. So calculate the percent mass of platinum in gold in a gold ring with 14 grams of gold and 4.5 grams of platinum. So it's 4.5 grams of platinum. That would be the solute. The solution would be 14 grams of gold plus 4.5 grams of platinum. It's the combination of them both times 100. Turns out to come out to be 24.32% platinum, which is probably the percentage of platinum in what they call white gold. And if parts per thousand and parts per million, you hear this a lot. Water sample contains so many parts per million lead or arsenic. A percentage is the number of parts of solute in 100 parts. So to do parts per thousand, instead of multiplying by 100, we multiply by 1,000. It's the same formula, except instead of 100, it's 1,000. Parts per million would be grams of solute divided by grams of solution times 1,000,000, 10 to the 6th. So again, they're usually used for very dilute solutions, like when you get your water report from the city, you know, so many parts per lead, parts per million lead, and then unless you're in Flint, Michigan, where it's probably grams of lead, because, well, I'm sorry, but, you know.
I mean, that's not.
I feel sorry for those people, but I mean, uh-oh, here come the moles. Of course. So chemical equations represent the number of moles of reactants producing products, because they react in moles. So we represent the concentrations on what's called a molar basis. So we're going to identify a new term here. Molarity. It's this italicized capital M. It's the moles of solute per liter of solution. So chemists use this quite a bit. So calculate the molarity of a 2 liters of solution containing 5 moles of sodium hydroxide. So the molarity would be 5 moles divided by 2 liters, 2.5, they call molar, M-O-L-A-R, 2.5 molar. So, if 5 grams of glucose are dissolved in 100 mils of solution, calculate the molarity. Oh, first thing we have to do is figure out how many moles of glucose 5 grams is. So now we got to go back to our stoichiometric roadmap, grams to moles, divide by the molar mass, 180 grams per mole. We have 2.78 times 10 to the minus 2 moles. How many liters of solution do we have? We have 100 milliliters. How many liters do we have? Hundred milliliters is how many liters? It's what? No, it's not 1. It's not 10. Wrong way. 1/10, 0.1. One times 10 to the minus 1. So you still have to go back to that equation. The molarity is 2.78 times 10 to the minus 1 molar, or 0.278. Dilution. We use dilution a lot to prepare a less concentrated solution from a more concentrated one. We can use the equation, we're not going to go to here. M1 is the molarity of the solution before dilution. M2 is after dilution. V1 is the volume of solution before dilution. V2 is the volume of solution after dilution. And remember, molarity is moles divided by liters. So to do dilution, we don't change the number of moles, we just change the amount of solvent. We just add more solvent. So M1 V1 is equal to M2 V2. So knowing any 3 of those 4 terms, you can calculate the 4th. Okay. It's not any different than when we did titrations. Well, you didn't do titrations here. Okay, we haven't got that far yet. Calculate the molarity of a solution made by diluting 0.050 liters of a 0.10 molar HCl solution to a volume of 1. Well, M1 we've identified as 0.1. M2 we don't know, because that's what we're looking for, the new concentration. The initial concentration was 0.05 liters. The final concentration was 1.0. We put those in the calculation. So M2 is equal to M1 V1 divided by V2. Just rearranging that equation. 0.1 times 0.05 divided by 1. 0.0050 M2, and that should not be here. This should be the concentration, 5.0 times 10 to the minus 3rd molar. Okay, questions? No? Okay. Pretty straightforward? No. Right? M1 V1 is equal to M2 V2. So divide both sides by V2 and you get this. And we identified M1 as being, this is M1. This was V1. This was V2. We just substitute them in the equation and do the math. I know you've all done this at home. Probably. So if you had like 1 quart of a 10% ammonia solution and you wanted to make a 5% ammonia solution, how much water would you add to it? 1 quart. So you'd have 2 quarts times 5% is equal to 1 quart times 10%. All right, let's stop and take. Now I'm going to talk about concentration-dependent solution properties. Those are, oh, this isn't going to work. Colligative properties. The properties of solutions depend on the concentration of the solute particles rather than the identity of the solute. So it doesn't matter what the solute is, it just matters how many particles there are. There's 4 colligative properties of solutions: vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. We're going to talk about each one. Vapor pressure of a liquid. What is the vapor pressure? If we look at Raoult's law in molecular terms, vapor pressure of a solution results from escape of solvent molecules from a liquid to a gas phase. Remember, molecules and atoms and that, they're always in motion. Kinetic molecular theory of gases and that. So here, if we have a container with a liquid and an empty space above it, and here's a pressure, this is a manometer measuring pressure, a certain number of the molecules of the liquid have enough energy to escape the surface and go into the empty space. While they're in the empty space, a certain number of them are going to lose energy and go back into solution. So eventually there's going to come a point when you have as many leaving solution as going back in. So we've reached dynamic equilibrium. When you do that, you measure the pressure. That is the vapor pressure of the liquid.
When you do what to measure the pressure?
We have a pressure gauge on it. And they're using a manometer here. So if you look at this, this actually is going to push, as the pressure builds up here, it's going to push the mercury down on this side and up on this side. So you can see it's here. That'll tell you the pressure. And that'll be millimeters of mercury, which you then can convert to atmosphere because you all know how to do that. You what?
No, I was just saying it's 2019. I don't know why they build machines that have to be converted to.
Oh, they don't. I mean, you just, certain industries use millimeters of mercury. Certain depending where you work, certain use atmosphere. Whether you're here or in Europe, use English units, metric units. Engineering uses Pascal because it's more of a historical thing than anything else. So presence of solute molecules hinders the escape of the solvent molecules. So this is just, let's say, pure solvent. Pick solvent, pick water, anything. It's going to have a certain vapor pressure. If instead now I make another one, and the rest of this is the same, and I put a solute in there that dissolves. Let's say sodium chloride or that. At the surface, I'm going to have go away. Go away. Some solute molecules. So what they're going to do is going to hinder the solid molecules from getting out because they're blocking the way. So I'm going to have fewer solvent molecules in the headspace. So if I have fewer molecules in the headspace, the vapor pressure is going to go down. So vapor pressure lowering. Adding a solute lowers the vapor pressure. It doesn't matter what the solute is, it just matters how many particles. It could be salt, it could be sugar, anything that dissolves in there.
Literally doesn't matter.
Literally doesn't matter. Okay. So when you add a non-volatile solute, something that isn't volatile like salt, sugar, that, the vapor pressure of the solid decreases in proportion to the concentration of the solute. So you kind of look in everything here. The solute are the red molecule, red pellets there. Oh, I lost my Wi-Fi. Serve as a barrier to the escape of the solvent molecules. So you have a decrease in the vapor pressure. They can't come out as much. Freezing point depression may be explained considering the equilibrium between solid and liquid states. Solute molecules interfere with the rate at which liquid water molecules associate to form the solid state. So when water freezes, when water freezes, it expands. So the water molecules actually have to get farther apart before they crystallize, which is why water expands when it freezes. When you have solute molecules, you add something to it. You're preventing the water molecules from getting out farther apart. So you depress the freezing point. It actually has to get colder. Freeze.
And this also doesn't matter.
It also doesn't matter. But we have to talk about the actual number of particles. So you'll see why there's a slight difference later on. The boiling point elevation can be explained because boiling point occurs as a temperature at which the vapor pressure of the liquid equals the atmospheric pressure. So if I have, whoops, let's go back up here.
You're not on the thing, you're not on the
You're not on the pen. There I go. You're right. Thank you. So here I have oh, shoot. Okay. Shoot that too. I want that. Okay. Here I have pure solvent. So it has a certain vapor pressure, okay? I'm going to say the vapor pressure is that much. Here I have a solution that has solute into it. So solute does what to the vapor pressure? Lowers it, so I don't have as much vapor pressure. Smaller arrow. Atmospheric pressure is coming down in both cases. Now to get to boiling, I have to make this equal to this. The vapor pressure equal to the atmospheric pressure. How do I raise the vapor pressure? The vapor pressure is caused by molecules leaving the liquid, right? So they have to have a certain energy. So I have to increase the energy to get more into the vapor. How can I increase the energy of the molecules? Do what? How do I make them move faster? Heat them. Yeah. So I raise the temperature. So here I only have to raise the temperature this much to get it to boil. Here, because I have a lower vapor pressure, I have to add more heat. Excuse me. So it increases the boiling point.
Is increasing that heat, is that increasing?
No, it's not increasing, not touching the solute at all. The solute is, but it's providing more energy to push past. So it's just like, let's say if there's two of us blocking the door and everybody else wanted to get out and you're just kind of moving.
More people got behind us.
But if there was a fire started in here, you'd be moving a lot faster. We wouldn't stand a chance to block you, okay? You'd be pushing out past us faster. So adding a solute lowers the freezing point, raises the boiling point. So this comes in handy if I could add a non-volatile solute to water. I would lower the freezing point of the solution, raise the point. And we essentially non-volatile to water in a 50-50 mixture. Antifreeze. Antifreeze functions two ways. In the winter, it lowers the freezing point. If you just had pure water in your radiator, maybe not down here, but up north, and it got 10 below, your radiator would crack because water expands. In the summertime, down here, you run on I-40, and it's 98 degrees outside, just water, you would bust open. It raises the boiling point. So that's antifreeze raises the boiling point, lowers the freezing point. Okay. In the winter, they spray the roads with saline solution, salt solution, because the salt is solutes dissolved in there. So when the water hits before it freezes, now you have lowers the freezing point. That works till about -10, -20. Then it gets too cold where it's not going to help much, which is why they also put sand out there. Sand just provides traction. Freezing point depression, delta TF, the F stands for freezing point, is proportional to the number of solute particles. Solute particles, not just solute. There is a difference. So if we look at NaCl, it affects the freezing point twice as much as glucose. Why? NaCl is ionic, so it goes to Na plus C minus in solution. Glucose is molecular. It doesn't come apart. So for every particle of NaCl I get, how many particles do I get in solution? 2. For every particle of glucose I get, how many do I get in solution? 1. So therefore it makes a difference what you're putting in. NaCl gives me 2 particles per particle. Glucose only gives me 1 per particle. So NaCl will affect the freezing point twice as much as glucose based on, if I start with 1 and 1 of this, because I have more particles. Each solvent has a unique freezing point, depression constant, or proportionality factor called Kf. So that is for each solvent. Boiling point elevation, again, the TB, the B means boiling point. Again, is proportional to the number of solute particles. An electrolyte will affect the boiling point to a greater degree than a non-electrolyte because you get more particles. So again, if I look at, and it's the same formula except we're using a boiling point elevation constant. So again, if I use NaCl, I get Na plus Cl minus. So if I start with 1 here, I get 2 here. C6H12O6 goes to C6H12O6. If I start with 1 here, I end up with 1. If I were to use something like calcium chloride, Cl minus plus Cl minus. If I start with 1 here, I end up with 3 on this side, 3 particles. So calcium chloride is even more efficient at lowering the freezing point. And a lot of times if you go to the grocery store, you see that comes in a little bottle. De-ice your driveways in that. You can buy it. That's calcium chloride in there. Now, they don't use that on roads because it's more expensive. Salt's cheap. Go to the ocean and let the water evaporate. You got the brine there. That's where all that comes from. You couldn't throw calcium chloride out there. But yes, you can go, if you got ice on your sidewalk, on your steps, you can take your salt shaker and go out and just throw it on there. Okay, that'll work. It doesn't melt the ice. What it does is there's always some water on there. It dissolves in the water, lowers the freezing point, it just spreads and then. Molality, which is different than molarity. Molality is a small italicized m, is moles of solute per kilogram of solvent. So again, molarity were moles of solute per liter of solution. Molality is moles of solute per kilogram of solvent. What? Yes. Yes, exactly. But not a solution of the solvent. Some types of membranes appear impervious to matter but actually have a network of small holes called pores. Our skin, for example. So the pores may be large enough to permit small solvent molecules to move from one side of the membrane to the other. Solute molecules can't get across because they're too large. So semi-permeable membranes allow solvent but not solute to diffuse from one side to another. So I'm going to actually draw this out. So here I have a tube filled and a semi-permeable membrane on the bottom, filled with a solution of high concentration, a lot of solute in there, here, surrounded by a solution that's very dilute. I have atmospheric pressure pushing down on this, and actually this is kind of open here. So as this pushes down, the solvent molecules go from the more dilute to the more concentrated. So the solvent molecules actually go up this way and fill up the tube. So what happens to the water in the tube? It goes up, right? So this is going to go up. So as the water in the tube goes up, the weight pushing down does what? Increase or decrease?
The weight pushing down.
Yeah, for the water in the tube. As it gets higher and higher and higher, as you get more water in the tube, does the weight increase or decrease pushing down?
The weight of the tube.
Weight of the water in the tube. Of course it increases. Because if I held your hands out and I put a book in there and I kept adding books, it would be pushing down. Well, okay. Don't know where the 9 came from or the G. But there comes a point when the weight pushing down equals the force of the solvent trying to go up. That's the osmotic pressure. So the water goes from the more dilute side to the more concentrated side. So that's what's called osmosis. The solvent goes from dilute to more concentrated solution through a semi-permeable membrane. To stop that flow requires pressure, like the tube water pushing down. Once you stop that flow, that's the osmotic pressure of that system. The osmotic pressure, symbol pi, is equal to mRT, where m is molarity, r is our favorite gas constant, 0.0821, and T is temperature in Kelvin. Yes. Osmolarity is the molarity of particles in solution. The osmol is used for osmotic pressure calculations. Okay. Calculate the osmolarity of 5.0 times 10 to the minus third molar sodium phosphate. So it's an ionic compound. So this comes apart to give you 3 of these and 1 of these. So essentially from 1 particle we get 4 particles, right? So if I start from 1, I get 4. If I start with 2, I get If I start with 1, I get 4. Yes, if I start with 2, I get 8. If I start with 3, I get 12. Okay. So I just took whatever I start with and multiplied it by 4, right? So if I start with 5.0 times 10 to the minus 13, to figure out how many particles I'm going to get, I'm going to do what? Multiply it by 4. And it turns out it's 2.0 times 10 to the minus 2. That's the osmolarity. That takes into account the effect that you have for ionic particles dissociating. If you went back to the boiling point, freezing point depressions and elevation calculations, there's another factor you have to put in there called I, the Van Hoff factor, which takes into account the osmolarity. But I don't think we're going to do that here. So calculate the osmotic pressure of a 5.0 times 10 to the minus 2 molar solution of NaCl 25 degrees C, 298 K. The osmolarity would be 5 times 10 to the minus 2 times 2, because we get 2 particles for sodium chloride. So M is 1.0 times 10 to the minus 1. We put that in the equation. This is M. There's R. T. The osmotic pressure is 2.4 atmospheres. Or almost 2.5 times atmospheric pressure. So let me go back here. And let me do some fancy drawing here. Oh, I hate this. Pen. Stay. 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 So this is obviously, on the left, it's obviously what? It's red blood cell. It's a red blood cell. To me it was. Okay. So you're out in the ocean, the motor on your boat, you're in a sailboat, the motor quits, the sail breaks, you're floating out there and you get thirsty. Well, you're surrounded by water. So you start drinking the water. What happens is after a while, your plasma around your cell gets a lot of particles in it, right? Salt particles and that. Inside, you have fewer of the, inside the cell, you have fewer particles. The cell membrane is semi-permeable. So the water, which is the solvent, is going to go from where to where? Yeah, so it's going to go from here, here. What's going to happen to the cell as you remove the water? Shrinks. That's a process called crenation. And you die. Wait a minute. We're going the other way. Don't get ahead of me. So they get you in time. They take you to the hospital. So the nice friendly nurse says, well, we're going to dilute that out. We're going to hook you up to IV of distilled water. So after a while, your plasma has very few particles in it. Your red blood cell has a lot of particles. The water's going to go into the cell. The cell's going to expand until it ruptures. That's called hemolysis. And you die. So one is from having a solution that has too many particles in it. The other one's from a solution that has not enough. Too many particles, this is called a hypertonic. Too few particles is hypotonic. What you want to have is a solution that has the same number of particles as inside your cells. And that would be called isotonic. And it's either D5W or 0.95% saline. So if you ever watch the old shows like Emergency or that, they stop somebody, you know, they call in, they said, hook them up to D5W. That's 5% water. The D is dextrose, the 5 means 5%, the W is water. Those are isotonic solutions. They won't cause your cells to rupture. Okay? So basically that's what this says. ISO means the same as. So if you ever watch weather reports and they say, here's, you know, you got these lines, these continuous contour lines on there, they see those are isobars, those are areas of the same pressure. Back a few years ago when the craze started for everybody, you know, we got to drink water, you know, we got to drink, you know, 1,600 glasses a day of water, stay hydrated. Everybody's drinking bottled water and that. A lot of people, you know, they want to make sure their water is safe to drink. Right? Problem is, it's still large or anything in it. It's got no particles. So people are going around drinking. You see these people, these big people drinking. They had 2 liters. They were actually killing themselves, literally, because they were hypotonic plasma. They're hemolysis. They were rupturing their blood cells. They're going into deep distress because, but I'm drinking water. Yeah, you're drinking the water. You need to drink, the Deer Park that has the deer poop in it, and the Aquafina, which means the end of water. Okay, you need, or just tap water, which has plenty of particles in it. So, what? In the Flint? Yeah. Well, I don't know if the water will come out of the tap in Flint. It's got so much lead in it. Okay. So, I don't know. This didn't transfer very good, but A is crenation. I think B is isotonic and C is hemolysis. I'm not sure, but we use this every day in other terms. So, can anybody think of where we might use osmosis? Especially putting something in a hypertonic solution. Do what? No. No, it's a product a lot of us buy. We use it to make this. Mount Olive, you would tell me? Pickles. That's how you pickle something. So there we go. So you put it in brine, which is a salt solution. You get the nice cucumber, and what does it do? It shrivels up. So, no. Jerky is a drying process. So you dry the meat, and I think you actually add salt to it in a lot of cases.
It's not dehydrated?
But drying is dehydration.
So,
Yeah.
so it's not true.
Yeah, it is.
So it's not the same?
It's not quite the same. It's not by an osmotic pressure.
Oh, okay.
Okay. But that's somehow they used to, in the old days, they would salt pork or that they'd put meat and salt in it. Because that would make an environment, they remove the water from it, at least on the outside. You ever see salt pork? It's real hard on the outside. Salt ham, country ham. Did you ever eat country ham?
No.
Don't. Oh my God, it's like, salty. But it doesn't provide a good area for bacteria to grow. Usually you have to, if you're going to cook a country ham, usually you have to soak it in water for 3 years or something. I don't know what it is. It's mostly a southern thing, but they don't use that up north because we have refrigeration up there. Buffalo this time of year, you just open the door and put it out back. So you can pretty much pickle anything. You can pickle people. Cucumbers, cauliflower, pickled pig's feet. Have you ever seen that in the store? No, they pickled pig's feet. Got it all over in a little jar. Pickled eggs. You pickled eggs.
What does that taste like?
Something that I don't want to imagine.
It probably tastes like a salty egg.
Salty egg.
So, aqueous solutions. Water is often referred to as the universal solvent. So it's excellent for polar molecules, most abundant liquid on the Earth. 60% of your body is water. It transports ions, nutrients, and waste into and out of cells. It reacts as a solvent for biochemical reactions in cells and digestive tracts. And it's either a reactant or product in some biochemical processes. If you were taking 132, you would see how water comes into play quite often. And if you're not doing anything this summer, there's a plug. I'm teaching 132. It's 2 days a week. Monday, Wednesday. So electrolytes in solution. We talked about molarity, moles per liter. So that emphasizes the number of individual ions. We can also talk about equivalents per liter. The emphasis is on the charge. So 1 molar Na3PO4. What's the concentration of PO43 ions? Well, each Na3PO4 gives you 1 PO4. So it's a 1-to-1, so you get 1 molar PO4. But for each mole of Na3PO4, you get 3 Na pluses. So the concentration of Na plus is actually 3 molar. Yes? Everybody see that? No? Yes? Okay. So, Na3PO4 in the solution gives you 3 Na pluses plus 1 PO4 3 minus, right? That's how it comes apart. So for each one of these, I get one of these. So if I have 1 molar of this, I get 1 molar of this. For each one of these, I get 3 of these. So 1 molar of this actually gives me 3 molar. Yes? Okay. It's like we did before with the NaCl, giving you 2 particles. And the equivalent is defined by the charge. One equivalent of an ion is the molar mass of an ion in grams divided by the number of charges on the ion. Equivalence per liter is equal to equivalence per mole of ion times mole of ion per liter. The equivalent mole value of the ion is simply the number of charges on the ion, regardless of whether that charge is positive or negative. So what does that mean? Calculate the equivalent per liter of phosphate ion in a solution with 5.0 times 10 to the minus 3 phosphate. So we have 3 minus. So we have 3 charges. Plus or minus doesn't matter. So we have 3 charges, 3 moles of charge per mole of phosphate ion times the molar concentration. So the equivalence per liter is 1.5 times 10 to the minus 2 equivalents per liter. Right? This is the molarity. This is the equivalence per mole of ion. Each mole of that gives us 3 charges. In this case, it's negative. It could be positive. In this case, it's negative. So the total equivalence per liter is 3 times 5.0 times 10 to the minus third. You take the charge and multiply it by the molarity. So if I were to look at this, let's say, again, it was Na3. Sodium phosphate. What's the charge on sodium? Positive. So if I'm going to do positive, how many? 1. So I'd have 1 mole of charge per mole of Na plus. What would be the molar concentration of the phosphate, of the sodium ion? Well, if this is 1, this is how many? 3. So if this is 5.0 times 10 to the minus third, this would be 3 times 5.0 times 10 to the minus third, right? So I end up equivalents per liter for sodium. Same answer. It has to be the same. Right? Because even though you have 3 times the amount of Na plus in there, you only have 1 charge per it. The phosphate has 3 charges per unit. So to get the equivalent amount, you need 3 times the amount of sodium to get the equivalent charge as 1 phosphate. Okay? That didn't work right. Okay. Oh well. So 2 most important cations in the body are sodium and potassium. In your blood, and we're talking about milliequivalents, so it's all divided by 1,000. Sodium 135. Inside your cells, 3.5 to 5. Potassium is just the opposite. 10 in the blood, 125 in the cells. So active transport, and transporting of sodium and potassium ions across the cell membrane. Active transport is different than passive transport. Active transport requires energy. Passive transport is just like diffusion, just goes. So cellular energy must be expended to make concentration of ions different on each side of the cell membrane. How's that done? Large protein molecules embedded in the cell membrane. Do we have a picture? We don't have a picture. If you kind of look, if you look at a cell membrane, and this is a cell membrane, the inner and the outer membrane. Across the two, you have a protein molecule. And it's sort of like a tunnel. The what?
Oh, no, I'm just saying, what's your alcohol?
Unless you're,
Alcohol?
what about it?
Can't alcohol just pass through?
And mine is small enough. But this allows stuff to go through the membrane. Okay? But you need to, if you just had passive transport, eventually it'd be the same on both sides. You come to an equilibrium. Active transport, to get more on the outside, you just have to push it. And that's done through these proteins, sort of like little gates. So there's danger that occurs in the body when potassium and sodium, both in the blood and cells, become too high or too low. If the sodium ion is too low, decrease of urine output, dry mouth, flushed skin, fever. If it's too high, confusion, stupor, or coma. Which I think probably quite a few of you are having high sodium problems right now. Because you're either in a stupor, confused, or in coma. Potassium too high, death by heart failure. Potassium too low, death by heart failure. You don't have a lot of options there with the potassium. So again, that's what they use. Potassium chloride, which is a salt substitute, they use to kill people. If you send your dog to the farm, you know what I'm talking about? That's what, yeah, that's what they use. Stops your heart almost instantly. So. Two most important anions in the body are chloride and bicarbonate. So there, chloride deals with your acid-base balance, maintenance of osmotic pressure, and oxygen transport by hemoglobin. Bicarbonate is the form in which most waste CO2 is removed from your body. By the way, just as an offshoot, when you lose fat, where does it go? Somebody tell me. I don't think I've ever lost any, but they asked this question to doctors, and I think 93% of them couldn't answer it right. Anybody want to know? Kind of. When we lose fat, we're burning it, we're oxidizing. When you oxidize, remember we did balancing equations, anytime we had oxygen, the products were carbon dioxide and water. So you breathe it out and you pee it out. That's where it goes. Fat does not become muscle. Completely different cells. You can't turn fat into muscle, you can't turn muscle into fat.
Can you sweat it out too?
But that's breathing, that's pissing it out.
What?
She was saying,
Yeah, you can sweat it out too. I mean, we do it. Yeah, it's kind of, you excrete it. Just so that's where it goes. What?
running in.
Well, you can lose. Yeah, heat'll. You know, you can go in the sauna and lose a lot of water weight. As soon as you weigh water, it'll come back. But so a variety of proteins are also found in the blood as a colloidal suspension. So they include blood clotting factors and antibodies. There can also be albumins, which are a carrier of substances that cannot dissolve in water. Fats. We eat a lot of fat, like cookies and crackers. Just saying. Don't. You're not supposed to eat in here. You know you're not supposed to eat in here. Because I don't know what's on these benches. So. The blood also transports nutrients and waste products. So albumins carry nonpolar substances, proteins. Okay, we already did that. I don't know why they repeated it. And that's it.